Welcome back to Python for Scientific Computing 1. In today's video, we'll take a look at the Numerical Python library, also called Numpy for short. Numpy stands for Numerical Python, and it's a fundamental package for scientific computing. Numpy provides a new data structure called the multidimensional array object, and this multidimensional array object can be used to create 1D, 2D, and other multidimensional arrays. 1D arrays are very similar to lists in native Python, and 2D arrays are matrices or used for storing matrix type data. Higher dimensional arrays can also be stored, which is basically a stack of matrices. Numpy provides us with tools to work with this data, create some specialized matrices such as the identity matrix, and perform a wide range of matrix calculations such as finding the inverse. Numpy can also be used to reshape arrays, transpose data, and perform other such calculations as well. NumPy functions are built using C and take advantage of faster loops that the compiled language C provides over an interpretive language like Python. So using NumPy also brings in some speed enhancements to your numerical analysis tasks. NumPy has a vast ecosystem that supports many other packages such as SciPy, Pandas, TensorFlow, and others. For details, I urge you to visit www.numpy.org to learn more about this project. The basic data structure of NumPy is the NDARRAY. And of course, if you want to access this data structure, you must import NumPy because it's an external library. So we use the statement import NumPy as NP to import NumPy functionality into Python. When we say import, what we are doing is we're taking the library that is physically on your read-only memory or your hard drive, and we are putting that functionality into the random access memory or the active memory of the computer, so Python interpreter is able to access these functions. We use NP as an alias for NumPy. This allows us to not have to write NumPy each time. When we call its functionality, rather, we can simply use NP. The basic data structure of NumPy is the NDArray. NDArray builds on a Python list, but it only stores homogeneous data. Remember that a list can store heterogeneous data or data of more than one type, but that is not the case with NDArray. NDArray can be reshaped as necessary, so you can convert a 1D list to a 2D matrix or even a 3D array. You can perform transposition easily and perform other matrix tasks as well. NumPy not only gives you a new data structure, but it also builds on several other basic Python types and enhances them. For example, you have floating point numbers with a variety of different precisions, float 16, float 32, and float 64, which help you store data with various levels of accuracy for your calculations. ND arrays or NumPy arrays are mutable. In other words, you can programmatically change them once you have defined them. Reshaping arrays is a common task that we perform with NumPy. And to give you an example, I define a NumPy array A, which is obtained using np.array. Remember, I have first import NumPy as NP. So this NP is an object, and this object has a method called array, and that array requires me to pass in an argument, which is a list. So I'm passing in this list, and when I execute this, I see that I have created A, which has the data type of numpy.ndarray, which is the data structure that NumPy offers. I can look at individual elements of this list. So if I put A square bracket 0, then I'm accessing the first element, which is 1, and that has a data type of numpy.int64, which is a data structure that's also available in NumPy. I can look at a feature of this A. Remember, A is an object, so an object has a feature, and here I'm looking at A.shape. Notice if there is no parentheses, I'm trying to get a value of a feature. So the value here is 12. So it's a one-dimensional array with 12 elements. I can reshape this array into 4, 3. So rather than having it as 12 elements placed in a single dimension or along one axis, what I'm trying to do is now place these 12 elements, 4 along one axis and 3 along the other. And I end up getting a matrix of 4 rows and 3 columns, which is where I've shaped it from a 1D to a 2D. Similarly, I can reshape it as 2 times 2 comma 3, 2 comma 2 comma 3, which basically gives me an 3D array. So the first element of the shape is your axis 0. Second element of your shape is your axis 1. And then the third element of your shape is an axis 2. How many elements are along that axis 2? Arrays are also indexed, so you can obtain values of individual elements by accessing the index. Indices of arrays are always numbered from 0. The first index is inclusive, which means it always has an element at 0. And the last index that you specify is exclusive. It doesn't quite include that index, but includes every other index till it reaches that point. For example, I've created an NP array of 1, 2, 3, 4, and defined it into an object called A. So when I print the length of A, it is telling me that there are 4 elements. And if I printed A from 0, 3, I want 0, 1, and 2 elements printed. So 0, 1, and 2, it prints me 1, 2, and 3. Similarly, if I put 0, 4, it prints 0, 1, 2, 3. It quite doesn't go to 4, but goes till 4, the fourth index, not the 4 number here, and then provides me with 1, 2, 3, 4. So that's how the indexing works. The first index always starts at 0 and is inclusive. The last index it goes up till that index, but never quite gets there. It stops one shy of that. Python view provides a view of the data. So what this view does is it doesn't really own the data. It simply points to the memory location where the original data is stored. So any changes in the original data will change the view object and vice versa. So really the only difference between your view and your original data are the metadata associated with each of these objects. The view is not affected when the original array is mathematically manipulated or vice versa. So to take a quick example, again, I create a simple NP array A, and I create B, which is A.view. See, this view has parentheses, which means it's a method that's acting on that object A. And if I look at B, I get the same NP array 1, 2, 3, 4. So A and B essentially have the same, they are pointing to the same memory address where this 1, 2, 3, 4 is stored. Now, if I replace A of 0 is equal to 0 and check B, the B got replaced. So instead of having 1, 2, 3, 4, I have 0, 2, 3, 4. And if I say A is equal to B, if I'm doing a Boolean comparison using this double equal to, then I see that they're all true. So A is equal to B. Similarly, if I take B and take the second element of the B and replace it with 10, so this is 0, 1, 2, the 3 is getting replaced with a 10, I get A, which is 0, 2, 10, 4. So you can see that A has changed. Any changes that I make to A will affect B. Any changes I make to B will be affected by A. On the other hand, if I were to do some mathematical manipulation, here you see that A is 1, 2, 3, 4, and B is a view. And then I change by substitution. B of 0 through 4 is 5, 6, 7, 8. And if I print A and print B, notice that they both have 5, 6, 7, 8 because I'm changing via substitution. I'm substituting the number of each index here. Now, if I were to say A is equal to A plus 2, I am performing a mathematical operation on A. That is, I'm adding 2 to each element of the A. So my A is 5, 6, 7, 8. So 5 plus 2 is 7, 6 plus 2 is 8, 9, 7 plus 2 is 9, and 8 plus 2 is 10. But if I print B, nothing has changed. It's still 5, 6, 7, 8. So A and B, the view is not affected when the original array is mathematically manipulated or if B is mathematically manipulated. But if there is substitution, then whatever you make a change, whatever you substitute in A reflects in B and vice versa. Data copies, on the other hand, there is a physical copy made of the data. So the changes to the original array does not impact the copied array or vice versa, either via substitution or via manipulation. So again, I'm importing Numpy, NumPy is essentially 1, 2, 3, 4, and I'm importing each of them as integer 16. So I'm not taking up as much space. I'm just putting them as 16-bit integers. Now, if I print type of A and then print type of A of 0, which is the individual element, I'm going to see that A is of the class numpy.NDARRAY. This is a new data structure that NumPy provides to us, the NDARRAY data structure. And then A of 0 is numpy.int16, again saying that this int16 is a data structure or a data type coming from NumPy. Now I make a copy. So I say B is equal to A dot copy. And then I have parentheses, just like the view. Copy is a method. So that acts on object A. And my object A is of the type NP array type. And if I look at B, it is 1, 2, 3, 4 type. D type is equal to int16. Now, if I put B of 0 is equal to 5, I have changed the first element of B. So I have 5, 2, 3, 4. But if I look at A, it is still giving me 1, 2, 3, 4. So even though I have done substitution here to B, it doesn't affect A. This is because I'm not looking at a data view, but I'm looking at a copy. So keep track of these data views, and copies are very important because data views, if we do some substitution on the view, it changes your original element, and that may not be intended during your calculation. So make sure that you're using data views and data copies correctly when you perform numerical calculations. So to keep in mind, data views can change by mathematical manipulation and not substitution. A data copy can change via mathematical manipulation and substitution. Okay. A matrix is a 2D array. It's a special form of array, and it is used to represent rows and columns of data. Data have to be homogeneous. Typically, they're numbers. So I can create a matrix A by essentially starting with a list of lists. And then I'm going to create a mat, which is the matrix version of A, as np.matrix A. And if I type of a mat, I see that numpy.matrix is the data structure of it. amat.shape gives me 3, 3 because there are 3 sublists in this master list, and each of the sublist has 3 elements. So I have 3 rows corresponding to 3 sublists and 3 columns, each of which corresponds to the corresponding elements within those sublists. Again, if I do length of amat, I'm simply going to get 3 because this is simply looking at a list. Once you have a matrix object, you can perform a variety of different calculations with it, namely inverse, multiply, add, subtract, and others. Here's a quick example of how to do inverse. So I create A, which is basically a list of lists, and then I can say np.linalg.inv A. So np is my numpy. Numpy has another module called linalg, or linear algebra, and this linalg module has a method called inv_a. So you can see that there is a little bit of nesting going on here. np is my NumPy object. That NumPy object, I'm invoking a module, and then from that module, I'm invoking a function, inverse of A, and you can see that inverse of A is written in there. Similarly, I can have NumPy imported here. I have my A. I'm converting my B. I'm writing B as a matrix, which is 1, 3, 5. And if I print matrix B, I can see that it is printing 1, 3, 5. If I do the transpose of B, then you can see that it has taken that 1 row, 3 columns to 3 rows, 1 column. Okay. Now, if I do np.matmul, which is matrix multiplication of A comma BT, I can get the product, which is 35, 37, 43. When you do mathematical manipulations or matrix manipulations, particularly matrix multiplication, it's important to make sure that your matrices are in the right format, particularly for multiplication. If you want to multiply A with B, you need to make sure that A is an m by n matrix, m rows, n columns, and then B is equal to n by p matrix, which is n rows, p columns. So the number of columns of your first matrix must match the number of rows of the second matrix. and the resultant matrix that you're going to get is going to have the number of rows of the first matrix and the number of rows of the second matrix. So this mathematical requirement still is imposed when you work with matrix objects. NumPy uses the linalg module or the linear algebra module, and the module uses two other packages called BLAST and LAPACK to provide efficient linear algebra algorithms. So LAPACK stands for Linear Algebra Pack, and then BLAST stands for Basic Linear Algebra System. These are very well established linear algebra libraries that have been ported into Python for use with NumPy. NumPy also provides us with many universal functions. So you have NumPy versions of algebraic functions, trigonometric functions, Boolean functions. You can check out the ufuncs portion of NumPy, and that gives you all the functions that are available. Similarly, the linalg module has functions for matrix multiplications, including advanced methods like singular value decomposition and Cholesky decomposition. You can also apply functions to a slice of the data, either to a row or a column, by using the NumPy dot apply underscore along underscore axis to perform vectorized calculations. Now, most of the NumPy universal functions are vectorized, which means you can take the function and apply it on every element of your array, of your NumPy array, without having to write a for loop. And this is where NumPy not only makes the code smarter and easier to interpret, but also faster as well. Not only are NumPy's universal functions vectorized, but NumPy also provides us a way to vectorize user-defined functions. This comes in very handy because a vectorization allows us to avoid for loops and makes our syntax much cleaner. For example, if I were to define a function myfunc a comma b, if a is greater than b, I want to return a minus b, else I want to return a plus b. If I have a list of objects going from 0 to 10, and I say myfunc z comma 2, what I want to do is I want to apply this myfunc function to every element of z, where a value is taken from 0 to 10 in increments of 1, and then b is taken as 2. It gives me an array because this is not vectorized. On the other hand, if I were to take the same function and write my myfunc v, which is z comma 2. So essentially what I've done is I've created a myfunc v, which is essentially the same myfunc here, but I'm running it through np.vectorize to vectorize it. And then what if I create a z now, which is a list, and run it to this myfunc v, which is the vectorized version, I can have calculations done on an element by element basis of that list. So you can see that NumPy vectorization comes in very handy to reduce code clutter. So in summary, NumPy is a versatile library for performing matrix-based calculations, particularly 2D matrices. Useful to create 1D arrays and perform vectorized operations, so it cuts down on your loops. 3D and higher dimensional data can also be easily manipulated. This is becoming increasingly important as we start using to process image, data collected in space-time and such. NumPy provides several universal functions or ufuncs that are vectorized for use with NumPy arrays, trigonometric functions, algebraic functions, Boolean functions, and such. And NumPy can also be used to vectorize and apply function to slices of data, which reduces the use of for loops. So overall, NumPy is an extremely versatile library, and I encourage you to check out numpy.org to learn more about NumPy. But having a basic understanding of NumPy is critical, especially if you want to do modern day scientific computing. I hope you found this video useful. I will see you in the next video. Until then, goodbye.